are exposed to some dramatic wave impacts, and I'll show you some video a little bit later. This is an account from one of the lighthouses back in the 1800s. This is from the Eddystone Lighthouse, which is about 15 kilometres offshore from Plymouth. And at that time, the lighthouse keeper made notes in his log, and he described a particularly violent storm, and there was considerable motion of the cylinder glasses fixed in the lamps, and the tower appeared to jump as if it was resting on an elastic body. So it must have been terrifying to be on this rock lighthouse in the middle of the storm. More anecdotes. The Bishop Rock Lighthouse report: the lighthouse keepers or the engineers were awoken from their sleep by a severe wave impact, accompanied by a loud booming noise. And there was an oscillation of the tower, which was the same as a minor earthquake. And there was a groaning noise with a rattling, and in the cupboards, the glasses were chinking. And when they were sat down, the motion felt like a gentle rocking of the tower. So think about how old these towers are. And this was an observation just in 2014. So very recent. And so the authorities that look after these coastal structures are concerned about their survivability. So with climate change in our part of the planet, that means sea level rise. And with the water being deeper, it means that the waves can be larger before they break on these towers. So the situation is only going to get worse. And so in 2010, AECOM contacted the university because we'd done lots of work on developing wave loads on other coastal structures. And so they asked us if we could find out whether there was a relationship between the wave that was impacting the structure and then the motion of the structure. And did they need to be worried? Would these structures survive? And so we started with a pilot project on the Eddystone Lighthouse, and the red spot indicates the location of a lighthouse. Now, if you were an academic or a graduate student at the University of Plymouth, how would you design a pilot project to try to address some of the key research questions? What would some of the key questions be? I indicated that there's a wave load interacting with the structure, and the structure might be responding. It seems to be vibrating in some way. These are what we thought would be the sensible research questions. So what's the nature of the applied wave load? And we think about the first slides. Will it be pulsating? Will it be trapping an air pocket? Will it be trapping a small amount of air? How do the rock lighthouses respond to the load? So is there any elasticity in the tower? And how can an isolated lighthouse be instrumented to measure the structural response? So imagine the complication of this offshore lighthouse, no electricity from the land. What sort of instrumentation can you imagine setting up on that lighthouse? And then the big question for the lighthouse authorities is, will the lighthouses continue to be operationally safe? Or one day, might there be a big wave that causes the structure to fail? So this is what the pilot project entailed. We had field data. We also did some numerical structural modelling, and we did some hydrodynamic modelling. Now, this is what the Eddystone Lighthouse looks like. And you notice on the right-hand side that there's a stump of an earlier tower. And in fact, that earlier tower is now on the land in Plymouth. It's the famous icon for our city. And the reason why they took down that other tower was because the rock on which it was constructed was starting to break. And so the lighthouse was okay, but actually the rock was breaking. So they removed the smaller tower. And we now have on the left-hand side the new Eddystone Lighthouse that was built about 150 years ago. So quite modern for lighthouses. So the instrumentation, we thought about maybe having a wave buoy and some bathymetric survey. So our university has some boats and we could go out there and do some side scan sonar surveys and find out something about the underwater geometry. We thought about putting some pressure systems on the outside of the tower, maybe even having a two-dimensional electric film that gives you a spatial description of the pressures. And we also thought about having some cameras. So right at the very top of the tower, we have a helideck platform, and helicopters would land on that platform. And these were constructed about 50 years ago. And round the edge of the platform are some photovoltaic panels, and they provide some of the backup power for that lighthouse. In the base is a diesel generator, and mostly they will use the diesel power to power the light that warns the shipping, but also the other navigation equipment that's on these towers. And we thought about having a camera on this stump, because then we could photograph the wave impact on the actual lighthouse. We thought about having some sort of way of measuring the vibrations with accelerometers or some sort of actuator. However, we weren't able to do that because of several really important constraints. So there's very limited access via helicopter, and you have to go out with the Trinity House staff. So you can't just go down 3 stories down to your laboratory. It's not as simple as that. You have to arrange the visit maybe 6 months in advance. You have to fly by helicopter, and it's very expensive. And so whatever instrumentation solution you have, you need to make sure that it's reliable and it's not going to fail while you can't get to it. It's also a very hostile environment. Again, it's not like the laboratory, which has got nice fresh water in it. This is salt water, which is highly corrosive. And I'll show you in a moment in a video the fact that the salt water can go all the way to the top of the tower. But the biggest constraint for us was the low power availability. So when we discussed our instrumentation with the lighthouse authorities, they said that we could have an average of 30 watts. Now, 30 watts is nothing. 30 watts won't power a PC, it won't power a normal digital acquisition system. And so we had to start thinking a little more innovatively and appropriate to the location. Regarding the idea for having a camera on the stump, well, this is what the stump looked like after some big winter storms. And you can see that more blocks have been lost from this stump. And so it was a good move actually not to put cameras on that stump. Otherwise the camera will be lost also with the wave impacts. In terms of the environmental data, we used some wave buoy data that exists from the Channel Coastal Observatory. So the Channel Coastal Observatory in the UK have a large number of buoys that are situated maybe 1 or 2 kilometres offshore, maybe up to 10 kilometres offshore. And they acquire a lot of data, and they've been doing that now for maybe nearly 20 years. And so there's a very rich data set that we can use. So we don't necessarily have to put our own buoy out at sea. We can use one of these Channel Coastal Observatory buoys. And then the Met Office also has some useful data that we can use. In terms of the bathymetry, we did go out and we did some bathymetry observations. So we had a master's student, in fact, who went out on a boat and was able to acquire this really helpful data set. So here in the image, you can see the surface piercing rocks. Now, this would have been done at high tide. So there's a large tidal variation there. So if you take the small boat out at high tide, then you can get a good scan of all of the rocks. And then in terms of getting the structural measurements, rather than using a high-power accelerometer and complicated digital acquisition system, we used what's called a geophone. Now, a geophone is more commonly used by geologists for measuring seismic motions from earthquakes, and it provides velocity time histories. But you know, your engineers, from velocity time histories, you can also get acceleration time histories, and you can get displacement time histories. So those velocity data were very valuable to us. And it communicated with us just by a mobile phone network. So it didn't require any high power. And then we did put a camera system on the helideck platform. So right at the top of the tower, we had 4 quite small cameras that we placed in scaffold poles. And then we fixed the scaffold poles to the metal lattice of the helideck platform. And we recorded data at either 1 frame per second or up to 5 frames per second. So the cameras, as soon as they were switched on during a storm, and we would have line of sight via this wireless communication system that went all the way to the university campus. So as soon as we switched it on during the storm, then we would acquire data at 1 frame per second. But then the downward looking camera, if it detected waves going over the bottom of the tower, it would increase the frame rate up to 5 frames per second. And we could control this remotely, as I said. And so annually, on average, we required less than 30 watts of power. So we actually had quite a sophisticated system, even despite the constraints. And these were the images taken from the lighthouse. So in the top left, you can see one of the lines of rocks that's at that location. Top right, you can see the stump of the old lighthouse. And then bottom left is another view, and there's a downward pointing view. So this is far southwest, and I think that this was maybe the near southwest. And we've got some footage, which I hope will play. Oh, it doesn't play on this laptop. We tried it earlier on my laptop. Ah, great. So I just click on there. Thank you. Thanks, Bo. So this was a particular storm on the 6th of January in 2014, so about 10 years ago now. And the waves are going to come from top left towards the lighthouse. And there's a couple of quite large waves. And then if you look, you can see the crest of a really large wave coming in. This is not the biggest yet. And as you look down, you can see a little window on the tower. Here's the big one coming in. Now, some of the larger waves, and that's not the largest that we recorded, would actually come up as high as the cameras and would obscure the cameras completely. So even though we calibrated the outside of the lighthouse, we put a checkerboard so that we could calibrate the camera images. We were hoping to get the wave run up from these video images. But when the waves were really big and there was a lot of white water, then the white obscured the cameras. And so we've got some wave run up data on the lighthouse, but not from the very largest waves. Now, in the winter storms of 2013-14, the UK was really battered with a whole sequence of storms. And in the location of the Eddystone Lighthouse, there were about 20 storms in a row, one about every week or so. And from that data set, we were able to acquire lots of impacts on the lighthouse. So top right shows you the significant wave height as a function of the date. So you can see that from October, November, December, January, February, there were some great peaks in the significant wave heights. So in those storms, we acquired a lot of really rich data. And the bar chart that you can see on bottom left is the number of events, and then horizontally, the maximum velocity. So essentially, the further you are over to the right-hand side, those are the very largest impacts. So most of them were fairly modest in size. So these are the velocities in millimeters per second, but there were some quite significant velocities. And actually, human beings don't really respond to velocities. We respond to accelerations. We're much more sensitive to those. So I'll show you accelerations in a moment. If we look at the influence of the wave parameters, on the left-hand and vertical axis, we've got the maximum velocity going up to 12 millimeters per second, and we've got the significant wave height. Now, why should it be that some of the very largest significant wave heights, they produce quite small velocities? I wonder whether you can imagine why that might be. You might think that actually the very largest wave heights should have the largest velocity, shouldn't they? The reason is because we got a large tidal range there. So if the storm happened at low tide, then the wave impacts are just at the very bottom of the tower, and they don't cause the tower to shake too much. But some of the storms, even though their significant wave height is more modest, because the tide is high, the breaking wave impact goes higher up the structure and causes more vibration. And here's a plot of the displacement now. So we've done can I remember whether it's the derivative or, anyway, we obtained the maximum displacement in millimeters. So look at the tiny sizes of these displacements. And this is plotted as a function of the Iribarren number. So you'll be familiar with the Iribarren number classification. So within particular ranges, you would typically have a spilling type wave, or a plunging wave impact, or a collapsing wave impact. And depending on the type of wave that you have, you'll get more or less amount of air that's trapped in there. So most of the interactions that caused any significant displacement were of the plunging wave type. The influence of the water depth. So this is what I was saying about the tidal variation is very important. So here we've got the maximum displacement as a function of water depth at the toe. And you can see that there is a maximum envelope here. And in order to work out these levels, we had to look at some of the old datum charts and compare it with photographs taken by kayakers. So we had the old drawings of the lighthouse, and depending on when the kayakers took the photograph, that precise moment in time, we were able to relate that to the tidal level. Another important factor at that location is the direction of the wave. So here we've got plotted the maximum displacement as a function of the wave direction. So in the UK, in the southwest, the predominant wave direction is from the Atlantic, so from the southwest or the westerly direction. But we have a complication at this site that we have these surface piercing rocks. So these rocks will inhibit the waves coming in certain directions. And there's just a schematic down the bottom that just shows what happens to waves coming from different directions. So essentially, if you're coming from this direction, this particular rock would shelter some of the interactions. You need this, this sweet spot where the waves come through between the rocks and then they smash the lighthouse really hard. And so most of the large wave impacts happened at this angle, 217 to 250. Now, in terms of the accelerations, which is what human beings can feel and what engineers normally use, these are the accelerations. And this is a typical vibration event caused by an interaction. And if we compare this to acceleration due to gravity, this gives a value of 0.1 G. This is not the largest. On other lighthouses, we've measured at the 0.2 G. And in fact, that is similar to a small earthquake. So it's no surprise that in the past, the lighthouse engineers said it felt like an earthquake, because actually that's what it does feel like. That's what the acceleration is equivalent to. So even though the displacements are really tiny, the accelerations are actually quite high. In terms of the structural numerical modelling that we did, for this pilot project, it was very simple. We just produced a finite element model. And there we assumed that there was a monolithic structure, which is not a very accurate way to model this, because actually this structure comprises lots of individual masonry blocks that are interlocking. So in fact, there's some elasticity there. But as I said, this was just the pilot that was 10 years ago, and we did much more advanced modelling more recently. This is what the model output compared to the geophone. So the geophone on the lighthouse measured a response at about 8 Hertz, and we weren't able to generate that in the numerical model, despite we thought putting in the accurate wave load. And we found out in the later project that I won't have time to go through in much detail, that the missing 8 Hertz agreement comes from the helideck platform. So the metal lattice that's on top of the tower actually has some implications for the vibration of the whole of the tower. And we didn't model that in the simple pilot project. And just a little bit more, I'll skip through this. So that was the original publication. And on the basis of that, we ran a much more comprehensive investigation. And rather than just the University of Plymouth, we also had University College London, and they did some of their vibration testing, and the University of Exeter. At Plymouth, we led the project, I led the project, and we specialised in the hydrodynamic modelling. So we had a sequence of different types of investigations: field modal testing, Exeter; long-term monitoring, that was Exeter and Plymouth; the structural analysis, and here we used more sophisticated modelling, including discrete element modelling, and then the hydrodynamic, which I'm sure will be most of interest. In terms of the field modal testing, this is an image of the British Isles, and these are the locations of the lighthouses that we tested. And we're currently doing some testing and modelling of the Skerryvore lighthouse that we've also done the Dubartak in the past. And so we ended up flying out to all of these helicopters, or all these lighthouses by helicopter, landing on them, and then shaking them. And we got in the newspaper because they thought it was a bit radical that we would be shaking these towers. They didn't understand the physics of it. We weren't actually going to damage it. We used this equipment here. So it's about 60 kilograms. So it's flown out by helicopter. If you have to access the lighthouse from the bottom, it's very heavy equipment to carry 60 kilos up through all the ladders. So the actuator goes at the top and does the vibration, applies some sort of known frequency. And then there are a series of accelerometers that are on the different levels of the tower. And then you have some sort of response. And this is just a quick illustration of each of the individual lines corresponds to an accelerometer at a different elevation in the lighthouse. And you can see some clear response frequencies. And that was written up in this paper. Just skipping on quickly because we don't have too much time on this. The long-term monitoring. So here again, we had the same constraints as the Eddystone Lighthouse where we did the pilot project. And we decided that we would like to have more quantitative data about the wave loading. So we ended up having 2 cameras that were very nearly set in parallel, and we used a photogrammetry method to find from the resulting images what the height of the waves were. and we worked together with Dr. Alvisa Benetazzo from Italy, and the communications were via SMS messages. So here are the locations of the two cameras, and this would be a typical example. We can get quantitative data from these images because of the setup of the cameras. Some of the key findings were that the wave impacts exceeded 0.2 G, and the lighthouse authorities can use this data to make operational decisions. Structural analysis I'll go through really quickly. This gives an indication of the discrete or distinct element model. So we discovered that the finite element model was not sufficient to get good data. And so we modeled each of the individual blocks, the interlocking blocks, and only by modeling each of the individual blocks can you properly understand the structural response. So we did limit analysis on the left, some more finite element modeling, mainly just of the helideck structure, and then discrete element modeling of the tower itself. And I'm just going to skip through this and get onto the hydrodynamic now in the last 5 or 10 minutes. So this is a picture of our ocean basin at the University of Plymouth with the instrumentation gantry. I'll skip this. So we did a series of experiments. The top of this slide shows simple 2-dimensional experiments on a cylinder that was instrumented to record the pressures and the surface elevations. The middle shows where we went 3-dimensional in our coastal basin, and the bottom shows the ocean model. And we had a drone survey done of the Wolf Rock Lighthouse so that we could get the data in order to actually construct a small-scale model for our ocean basin. So in our 3D tests, this is a time-lapse video. And you might think, oh, where's the water? Well, in our ocean basin, we have a floor that can be raised right up out of the water. And so we can construct the model and the accurate bathymetry on the floor. And then when that's completed, we lower the floor back into the water. So here they have nearly finished the construction of the rock. And the lighthouse will go in this location here. There we go. And now they're just going to clear away this. And then the floor will be lowered. It'll be lowered to the appropriate depth to do 1 in 40 scale model tests. Now, the instrumentation that we had total force from a 6 degree of freedom load cell. We had 12 pressure transducers along the center line and around the side. We had an optical tracking system. We had surface elevation gauges, and we had high-speed camera. Now, one of the issues with measuring forces is the forces get mixed up with the experimental effects. And so you need to have ways to separate the real forces from just the laboratory effects. And this is a paper where we described how we would do that. The next slide shows a video of, on the right-hand side are the surface elevation wave gauges. The wave is going to come from right to left, and you can see the interaction of the waves with the lighthouse. And you might think, oh no, you wouldn't have waves that big, but you do get waves that big at that location. And you can just see the helideck at the top here, and there is some vibration from the moving floor, so we have to separate that out. But when we go out to these lighthouses, sometimes we find that there is damage right up here from the wave impacts. We then painted the lighthouse for public engagement so that we can show the lighthouse to school children and tell them about wave impacts on lighthouses. Here's just a few graphs showing the measured forces as a function of wave height. We generated regular waves where each of the peaks is identical. And we also created focused wave groups where we just run a transient wave packet. And we looked at extreme waves up to 1 in 250 year extremes. and we measured the forces. And we found out that compared to the best wave load equations that we have for this type of situation, the wave impacts are much longer than the theory would suggest. We also did some CFD modeling using open foam. So you can imagine that if you are creating a physical model, it takes a long time for that setup, that you can change your numerical model rather quicker. And so you can look at models with different water depths, with different surface gradients, with different wave heights. And so using machine learning, we ran 81 different configurations in order to produce some sort of generic equation. Just going to skip that one. The latest news, just a month or so ago, there was a collision of a large vessel with the lighthouse. So this is the track of the Mazarine. So it's a container ship. I think it's 31,000 ton. It lost its power and it gradually drifted towards this famous lighthouse. And then it turned around and then it floated away in a slightly different direction. And this is what it looked like from the Coast Guard perspective. So you can see the size of that ship behind the lighthouse. And the lighthouse authorities were very concerned about the damage to this lighthouse. But because we had been measuring accelerations on this lighthouse before the collision and then after the collision, we could look at the structural characteristics and we could reassure the lighthouse authorities actually no damage has been done because the structural characteristics are identical. And then if you'd like to find out more information, you can go to the Stormlamp website. There's a lot more to our investigations than what I've just presented to you. So yes, I think I'll end with that. So thank you to Professor Ma for his kind invitation to visit DUT.
Thanks, Professor, for the next presentation. Next is the Q&A session. For the online audience, if you have any question, you can turn on your microphone to communicate with the professor. For the offline audience, if you have any question, you can raise your hand up. So is there any questions or comments?
Okay. Question about experiment that you have done about the lighthouse with a small scale. And you take the various data about your point. Oh yes, this page.
Okay.
Let me see that your works has made virus deep. Just familiar with the really deep as its lighthouse location. Located. And how long did you make this model from the beginning to the end?
That's a good question. It was quite complex to construct. So the lighthouse itself was 3D printed, and I think it was in 10 individual elements. Even the details of the helideck structure were 3D printed. But also it was complicated because inside the core of the lighthouse, we had instruments to measure the force and the moment. And we also had the screw fixings for the pressure transducers. So all of that was in the 3D printed model. And then the bathymetry was constructed from this marine ply as accurately as possible. So we had the survey data. Thank you. We had the survey data, and then we constructed the bathymetry in the laboratory. We had vertical fins that we then covered over with flexible marine ply. and then we painted all of it with resin. So the actual construction in the laboratory, maybe it was over 1 week. It was slightly extended because of a little problem. When they originally did the painting of the resin, they used the wrong mix and it ended up just being sticky. So they had to do it all again in order to make it nice and smooth before we could put the water back in. So yeah, it was a lot of time in the planning. We had some fantastic postdoctoral researchers who did this. And also in our laboratory, we have amazing technicians. So our technicians have PhDs. They're very keen to help. So yeah, it was great to do this experiment, but it was quite challenging.
It's really complicated models.
Yes.
Thank you.
One question. It's the branches in and the question is that you use the FEM model to model the lighthouse. The response will pack. What's the hydrodynamics parameters input to the FEM model?
Yeah, so there were 2 stages of numerical modelling. The initial pilot stage, where we just did a finite element model, which was very simplistic. The wave loading that we used was based upon the theory of Weinke and Umarachi. So that theory is based around cylinders surrounded by deep water or intermediate water depth, which is in fact not very accurate for this configuration, because here we have the water depth like a mound, like a rubble mound. And so that has some effect on the wave loading. So there is no good prediction formula for this configuration. It's similar in some ways to some gravity-based foundations for wind turbines. But again, there's no good equations for that. And then when we did the more complex modelling later on, and University College London were doing that, they also based it around the Weinke and Umarachi formula. But as I said, the experimental data that we acquired showed that the wave loads were not quite so high as the Weinke and Umarachi, but they were longer. So they're over a longer period of time.
There are questions in the chat box.
Okay.
Okay. Lots of questions.
Okay.
One.
Okay, so first question is, what problem can waves solve in a steep coastal structure? How to solve it? What problem can never be solved? What is the root cause? What problem can solve in steep coastal structure? Is that saying what is the research gap? Maybe I'm not sure I understand the question is asking. What problem can never be solved? I don't know. I think engineers would always suggest that we can always try to think harder or try different techniques in order to solve a problem. So I'm not sure whether a problem can never be solved. What is the only purpose and meaning of waves in steep coastal structures? The only purpose and meaning. I don't know whether something has got lost in translation here. Essentially, the way in which coastal structure interactions would differ from deep water interactions is there are greater non-linearities, and those non-linearities will cause more non-linear interactions. So essentially, it's more complex than in deep water. What is the only purpose and meaning of this topic? Well, coastal structures in general in the UK and in lots of parts of the world, they're there to protect infrastructure, to preserve the coastline. Next week, in fact, I'm giving a talk about a case study which will talk about how structures are used to preserve coastlines. So I scroll down. Could you give more details about the modelling broken wave in open foam? How about the agreement with the experiment? In addition, could you give more details about the machine learning? Yeah, I don't have the details of the open foam model just off the top of my head. We did it many years ago. We certainly did calibration tests from the coastal basin, and actually the forces were very good. They're very highly comparable. I don't know within what percent, but we have got that data. If you want to email me, I can show you some of the comparisons. The machine learning, again, that's work actually still being undertaken by Dr. Edward Ransley. So he leads the numerical wave structure interaction program at the University of Plymouth. So you could contact him for more information on that. What problem can waves solve in a steep coastal structure? How to solve it? Oh, that's the same one again, I think, isn't it? In addition, could you give some suggestions about protecting vertical cylinder structure from such extreme waves? Okay, so going back to the beginning of the presentation, if you can find some way of causing the waves to break before they interact with the structure, that's useful. But actually, you're probably thinking about other cylinders that may not experience these breaking wave impacts, because if they're in deep water, you don't tend to have very large breaking wave impacts, because the water depth is such that you won't have breaking according to depth. Just trying to think about other ways in which you might have reduced. I have seen some structures where there's a perforated jacket around the outside. So that is a way of transferring the load to the outer jacket and preserving the inner structure. I hope that has a couple of suggestions there.
So, okay, sorry. Is there any question or comments? Thanks. If no more questions, please stop here.
Yep.
Okay. Okay. If no more question, and due to the time limit, I think our Q&A session has to be end here. If you still have questions, I think you can contact Professor Alice through email after the meeting. Okay. Okay. At last, we have also prepared a certificate for the presentation. So we will provide Professor Ma, yes, to award the certificate to the professor.为什么没有梦？放光。
you.